LVW, right? Then anybody remember? Let's say this one has dimension n, that one has dimension m. All right? Then anybody remember what generates these vector spaces? All the transformations, right? Not necessarily matrix. These are not column vector spaces, right? Just abstract vector space V and W with dimension n and m. That was number one homework problem, although that was a column vector. So that was a Tij, Tik. Remember? Tik, these are the linear that most of the Tik sends most of the base member to 0. Only one thing is going to survive and go somewhere, right? Those are the things. So in my index, and I usually run through this the base n 1 through n, and m go through, k go through 1 through m. So there are n times m linear maps, and for the smaller size and actual size in your homework, you actually show that these are linearly independent. How was the homework problem? Was that all right? Problem number 1 of the one that you submitted today, right? Those were like 3, 4, something like that size. Were you able to show linearly independent? Yeah. So does that kind of make you believe that it's in general those things are linearly independent because of lots of zeros and everywhere, right? So would you believe that these are linearly independent? Tik. So let's recall. Tik send is all about if these are the base members V1 through Vn. These are the base members for that, and that one has a base member W1 through Wm, right? It's about where to send this Vi. Vi is going where? W something, right? Wk, that's where you're sending. And this one, Tik, send Vj to where? 0 if j is different from I. That's the definition of Tik, and that's so because of that, we believe the dimension of LVW is number of elements in the span if they're linearly independent, right? So n, which is dimension of V, and W and m, which is dimension of W. Although I didn't give you proof, that example, I hope you believe that these are linearly independent. Therefore, dimension of all the linear transform vector space of linear transformation from V to W is the dimension of V times dimension of W. All right, that's what we're doing, and then that's another thing we did last time. I introduced last time was this rank theorem. Is that right? What is the condition on that rank theorem about V and W? V and W are finite dimensional. Do you know an example of an infinite dimensional vector space? Polynomial. All polynomials infinite dimensional. So you have to kind of cut it down to degree less than 10, and then it becomes like this. And what was the first statement? And there is a t going from where to where? V to W. That's the 3 elements in here. Then what happens? That V is decomposed, right, into a null space of t, right? And direct sum, or the whatever left of it, V prime. And there is no unique choice of V prime. Second part is claiming that, what was the second part about? It's something about V prime. Remember the V prime? It was a dimension of the V prime is equal to dimension of, no, dimension of, right, dimension of a range of the whole map. All right, these guys are all mapped under T. These don't do anything. It just disappears, right? Only V prime survives. And if you can establish that none of the V primes dies, then it's kind of believable, right? It makes sense. And the most common part, they usually introduce without these first two parts, is that the dimension of V equals dimension of null space of T, right? Plus dimension of range of T, right? The whole thing, some part dies and some part survives. And put it together, dimension is the whole thing. That's what that is. I was introduced, and the long exercise number 3 is to kind of explain where you actually see this division in terms of echelon form, right? That was number 3, the point of number 3, plus a few more interesting observations. Today, this is the most important part. So we're going to prove on that. But isn't that 1 and 2 is stated like this? Isn't that obvious? 3 follows just immediately, right? Dimension of V is the dimension of null space plus dimension of B prime, but it's the same in here. So it's this immediate consequence of that. So let's prove 2. Here I'm using the idea of restriction, and that was used in the advanced problem today, right? So let's get used to this idea of restriction. Problem 2. So I'm writing down first B is, let me see, B is the basis of null space. B1 through Vm is a basis of null space of T, and B prime is V1 prime going through VL prime is a basis of V prime. That's all I want. Okay, so is that all right? V is decomposed as a direct sum to null space and V prime, and I wrote down the basis of a null space and wrote down the basis of a V prime, the complementary part. Okay, so what is the dimension in terms of like this, dimension of V? M plus L, is that right? M is your number of the basis in vectors here. L is a number of vectors here. M plus L is a dimension of V. That's what I wrote it down. Okay? Next thing to focus on is that the function T goes from V to W, right? And V prime is a subspace of V. So can we look at this T only apply to V prime? So this is what mathematicians do. Here, let T bar be a vector space from V prime to W. V prime is a subspace of V. Is that right? Be given by, is a funny part. T bar of V, which is coming from V prime, is equal to T of V for all vectors V coming from where? What are we plugging in here when you define the function T bar? I'm about to define this function going from V prime to W, and here's the formula. But where is this V is coming from when you define a function in this way? V is coming from where? V prime, that's right. V prime. That's the domain. We only have to give a meaning that if I have a vector in V prime, what are you going to do? Just use the original formula. Right. That it's an interesting thing happened of a null space of T bar. So that's what we're going to focus on. But this map T bar is called restriction of original map. So usual proof courses, they introduce like the T is the original function, right? That is defined on V, but subscript V prime is the notation they use in here. But unless there's like multiple subspace they play with, this is inconvenient notation for especially for typesetting. So T bar reduction, is that all right? Okay, it's like a polynomial restricted down to those number 0, 1, 2, 3, 4. Isn't that kind of analogous situation? Polynomial is defined all the real numbers. Now we're only looking at total polynomial on 0 to 3. Things like that. But here is a V is the full space, but we only consider the V prime. All right? Make sense? And what happens is I like to claim that, let me think about it. Let's go for one thing at a time. I'd like to show that this is injective. I think that's a fundamental thing that I have to go for. T bar is injective. How do you, anybody remember the proof of T being, I mean, there's of course two thing goes, that's a typical proof, but for vector spaces, there's some connection with it being T bar being injective versus something, right? Some theorem. T is injective if and only if null space. Anybody see the connection of null space T bar? Null space must be 0, right? All right. If it is injective, of course, nothing, no more than 2 elements go to 0, but the other direction is something you have to think about. Null space 0. So here's why. If proof is a T bar is a 0, so I'm looking for V is coming from B bar, right? So isn't that, because of the definition, T bar V is also T of V. Is that right? That's the definition. It's a 0. So what conclusion do we have? V is in null space of what? What conclusion do we have here? Null of T. Isn't that right? The T goes to 0 in here. So V is in a null of T, and also V is from where? V prime. So isn't V is inside a null T and V prime? But what do we know about null T and V prime? That's a direct sum. It's a trivial intersection. Okay? All right. So as previously thought out thinking process, so it's not that easy to organize like this. Well, anyway, so anybody remember, so this is injective, so let me claim that this V1 prime, anybody remember what these were, V1 prime to VL prime? These were a basis of V prime, right? And the map on these spaces is injective. So what about is a basis? What can you say about this list? T V1 prime, T VL prime. We're sending all this. Here I'm carefully using this parenthesis instead of a curly brace, because if there's a repeat of element in the curly brace, it changes to one element. So it changes from linearly independent to dependent to linearly independent. So if there's a repeat of element, you have to keep it in this ordered list. All right. So this is linearly independent. I want you to think about correct reasoning. Why, if I have linearly independent vectors are V1 prime to VL prime, right? If I send that along the linear transformation T bar, this remained linearly independent. Why is that? Not in general. Not in general. In this case, yes. So you have to find the reason why. So in general, it's not. Well, if these are linearly independent, in general, its image is not linearly independent. But under certain condition, it is linearly independent. And the correct answer, one of the correct answer, is that T is injective. Okay? So what we're trying to show, I think, is this guy. So I think we're just looking at V prime. That's where we are, right? So do we have a kind of answer to the V prime? Well, we know the V prime is L, right? We know the dimension of V prime is L. And that shows we are going for dimension of range of t, right? But what we have figured out here is, what is the conclusion you think by just looking at this statement? It's not about t, but it's something about t bar, right? So I forgot to mention that is a t bar. Maybe that's caused the problem. Isn't that a t bar here? Right. That's a t bar. It should be. T is correct because it's the same map, but the t bar is a better notation in here. So doesn't that show that dimension of range of t bar something, right? This is everything, v1 bar, v1 prime to vl prime. They're all centered along this one in here, and they're remaining linearly independent. So what is the dimension of range of t bar in this from in here? One of us said that is dimension of t bar is L. Someone else and try to explain it. Chris said that's L. Let's bring him down. Let's scrutinize this answer and see if L is not correct and something else is correct. Let's try that. L makes sense. Why? Because this is all you're going to get, and they're linearly independent. That's the basis, right? This is the basis. Linearly independent part is clear. How about this one spanning? Is that part clear? Linearly independent is stating right there. Why does this one span the range of t bar? That'll finish off the argument. Is that right? Why does that span the whole range of t bar? Everything is a linear combination of this one. That's going to be nicely translated linear combination of that one, right? Because t bar is linear. It's easy for me to say with a lot of checking things going on. Does that make sense? All right. So that goes to two things when you conclude this one, right? Span and linear independence. That was there, and I just said this linear span part. All right? So I guess I shouldn't do that. So if I have t bar, that everything looks like this, right? Vk prime, k going from 1 through where? L. Any element is going to look like this. I'm going to show that this one is generated by this guy, right? So linearity passes through all the addition. Is that correct? T of v plus w is a tv plus tw. So it passes all that summation as long as it's a finite. And linearity, you can pull out scalar out of it, right? So here is k1 through L of ak go outside and t of a vk prime. Isn't that right? So range, inside the range, everything looks like this. Image of a t bar, whatever the vector you pull out. But it can be rearranged as a linear combination of these vectors, right? What are these vectors? They are these vectors right here. So this is a1 t v1 prime, which is this member. Bar, I lost the bar again, sorry again. It's still correct, but bar is a better notation. Is there, and a2 all the way up to al t bar vl prime. Isn't that right? Therefore, whatever you have it in the image, the range is generated by the linear combination of these L guys. And we're claiming that it's linearly independent. Therefore, the dimension of t bar is L. Dimension of the range of t bar is L. Does that make sense? All right. Let's see one more thing. We want to claim, where is the theorem? Oh, claim d dimension v prime and the range of dimension of range of t. What we have shown in here is the dimension of v prime is L, and L is exactly the dimension of t bar, right? Range of t bar. So I can write down dimension of range of t bar here. If I can change that dimension of range of t bar to dimension of range of t, and that's it. Let's compare the third one. Range of t bar, not the dimension, versus range of t. We're going to compare these two things. The fact is that these two things that don't have the same dimension, but it's actually the same space. Okay? All right. So here's a range of t. That's what we wanted to target. Range of t looks like this. T of everything here, right? How does everything look like? T has a domain V, the full space, right? So how does the element look like inside V here? So this. I started with the B being the basis of null space, B prime the basis of V prime. If you're just pulling arbitrary element from V, then it's a linear combination of this one plus linear combination of that one, right? So can we write T as a linear combination from K through, anybody remember the number? I mean the index for null space? I think that was N. It was M actually. So that is M. So the null space has dimension M. Here's a VAK. VK, that's null space part, right? And what about the other one? K going from 1 through L. I have to use different coefficient. BK, VK prime that goes through. If you pull out any element from, what is it? V, they look like this. Some of the linear combination like that, right? So let's see what happened to those guys. That's everything you're going to get out of a range of t, right? You take an arbitrary element and send it along the t. Does that make sense? All right. So this one, let me just work on this one. Linearity sends this one in here. So we just looked at what happened with a linear map with a sigma. You see that t passes the sigma and also passes the scalar. So it goes to k1 through m, ak, tvk. Is that right? Plus, it also passes this summation and passes right to bk and tvk prime. Correct? All right. So our goal is to rearrange this one so that we show that everything in here is inside the range of t bar. So what do you think we should do in the next step to simplify this expression? They came from the null space, right? So what do we know about tvk? They're all 0, right? So they all disappear. So which is equal to, they're all zeros here. Therefore is equal to k going from 1 through L over bk tvk prime, right? Whatever you get is actually simply look like this. Okay? So what is the conclusion? We looked at all the elements in the range of t, and we're going to conclude something. And our goal was comparing these two spaces, right? Range of t bar versus range of t. How are they related as spaces, not the dimension. So what's the conclusion from here? We write down like this. Range of t is what we looked at, and it is compared it with the range of t bar. What is the operator that goes in between? Not direct sum. What's that? We can fix it if it's wrong. Does the subspace make sense? We looked at all the elements here, right? It looks like an element in the range of t bar. Isn't that the generator of t bar? Range of t bar, right? Range of t bar is generated by these guys right here, right? So I looked at some arbitrary element in range of t. I was able to show that that actually looks like well, actually wasn't clear. There's no t bar in there, right? That's maybe the problem. How do you change this t to t bar? Why is the t can change to t bar? You can't do that here, but you can do it here at the last stage. because t bar is equal to t as long as your input is coming from v prime, right? And you can't change it here. Your input is not from v prime, so t bar doesn't apply. But at this stage, everything is inside v prime, so you can switch to t bar. And so here's a t bar, so that explains this one. Maybe that was a difficulty for you to agree on this one. Does that make sense now? Yeah. So everything here is a linear, is an element in the range of t bar. Okay? But t bar is inside the W anyway. It's a restriction. So I claim this clear. We don't need any of this result to conclude range of t bar is actually contained in range of t. Because what you're going to get out of t bar is still what you're going to get out of t. That's a bigger one. So it's kind of sandwiched or whatever. So therefore we conclude range of t is equal to range of t bar. Is that right? In particular, we conclude dimension of range of t is equal to the dimension of range of t bar. But this is much more important statement than just they having the same dimension, right? Don't you think? This is a lot better result. So going back, this concludes the proof actually. So that was L, remember? They remain independent. So that was a dimension of v prime, that L. So therefore that proves the statement part 2 there. Okay? So what's behind it here, this statement, is really that range of t is the same as range of, t bar, which is restricted on that smaller part. You're going to get everything just with this v prime. You don't have to deal with that if you want to. Does that make sense? That's the rank theorem. Any question? No? All right, some examples. It's a good example. Remember P5? That's our V. All right? Degree less than or equal to 5. That's a polynomial. And T is coming from endomorphism of V. What's endomorphism of V? LVV, right? V going to V. Here's a polynomial P. I pulled it out. So here's my map. X times P triple prime plus P1 prime and P. Okay? This is a differential operator. You agree? That involves differential operator, the differential operators, right? Okay. So do you believe this is linear? I just wrote down operator. If I give you a function, you're going to differentiate 3 times and multiply by x, and plus the first derivative of input, and so on. You have to, this high order derivative is different linear operator, right? And multiplying fixed polynomial to something, that was also a linear operator. That was a T2 of early homomorphism. So it's a composition of linear operators, right? And composition of linear operators remain linear. Something that we had to check, but we never actually proved it. But that's the statement you have to probably remember. All right. So because of that, compositions of linear operators remain linear. This T is a linear. That's one way to explain this. Right? So, so here is some question I'd like to ask. Let's go for no space of T. Of course, I looked at it a little while and got this answer into 0. Can somebody explain why this one has null space 0? Of a degree of the polynomial. You see what happened to the degree of the polynomial? You bump it down to 3 times. You see what happened as you differentiate? And you bump it up by 1 by multiplying, right? How about this one? You bump down the degree by 1. How about this one? No change. So does that help you to see why the null space is 0? right? The degree, the highest term, is untouched by the other ones, right? How can that be 0? It has to be originally 0, right? Does that make sense? All right, so that's a homework. You good? All right, so let's apply this rank theorem. What is the dimension of V? Six. Thank you. I always make the mistake. It's a 5, but it's not. If you write down the coefficient, there's a 6 coefficient in there. So let's write that down as a what is it? Null space. The rank theorem. What does the rank theorem says? Dimension of null space of this map plus dimension of the rank of this map is supposed to be 6, right? But what is dimension of null space? 0. Therefore, what is the rank of this map? 6. Okay? So here is my question, is to prove. So the meaning of the rank being 6 here is used in the following problem. But the following problem doesn't seem like anything to do with that analysis in here. So here's a interesting part. X times y triple prime plus y prime plus y equals 52 times x to the 4th plus x squared plus 1 is a well-known differential equation. What do you think? X times y triple prime plus y prime plus y is equal to this function 52 times x to the 4th plus x squared plus 1. Differential equation, right? Ordinary linear differential equation is solvable. Is what you have to prove. And I'm saying rank being 6 has something to do with that. Okay? You see the connection? Rank 6. What is the... Can somebody come up with a conclusion of rank 6? If its rank is 6, T is... What kind of map is this? T is some S word. You know the S word for a function? There's I word and S word for a function. Surjective. Does that make sense? If a function is going from V to V, if your range has a dimension 6 and your whole thing is dimension 6, right? What can happen? Dimension 6. It has to be everything, right? If it is slightly smaller, dimension must be smaller. So that is dimension theory. Okay? So what has it got to do with the third problem here? So we have this V, which is degree of all 5 or less, right? And this T is just twisting and adding here, right? Is that right? And here sitting 52 times x to the 4th plus x squared plus 1. Isn't that the degree less than or equal to 5? Right? What is the surjective saying? Well, whatever you choose, there must be some sort of function in here that hits this one. So what is T? T is exactly that operator in this involved in here. Alright? So, because it's a surjective, there is a polynomial P in degree 5 polynomial or less, such that T of P is whatever you see in the right hand side of 52 times x to the 4th plus x squared plus 1. Right? Therefore, there must be a solutions because of the dimension theorem. In the theory of a differential equation, there is something called uniqueness in existence. And it does not use any of this linear algebraic structure. It's a hard analysis on the integral and things like that. And that is independent proof from this one. From there, you can conclude there is a solution using the uniqueness in existence. And here, using algebraic structure, you can also conclude if there is small spaces like that, whether there is how to determine this differential equation is solvable and this differential equation is not solvable and things like that. Okay? It's pretty neat. And it can come with it in that more setting. It has nothing to do with the setup, and it asks you to, all right, I am giving you this differential equation, and I want you to explain to me that x to the 71 plus 71 times x plus 71 is solvable. There's no v nothing. It's just differential equation, and we want to see if this is solvable. And then you enter p something, pm. What should be that pm is m. Maybe you have to go to degree less than or equal to 71, right? So what is the dimension of P71? (72), right? 72, and then you calculate the null space. When we calculate the null space, did we use anything about the dimension of the V? It was just the degree of the polynomial. It is a local property. So null space is still 0. Did you agree? Null space is still 0. Therefore, it must be surjective, right? If it is a surjective, whatever degree 71 or less, you pull it up here, there will be a function that hits that. So it's a solvable. Right? Yeah. What is it? That's a different question. But the solvability, the existence of solution, can be argued nicely using the dimension theory. That's pretty neat. The term linear in the differential equation precisely came from this operator being linear between the functions, right? So that's one of the application of this dimension theory. All right, here's that monster coming back again. Phi, remember phi map? Phi map was L going from V to W, dimension n and dimension m. What is that map going to? It's actually, in my watch, is 12, 13. Right? So we have more time. Where does that go to? Matrix space, right? These are not column vectors, not necessarily column vectors. It's actually column vectors. I was wrong. The one we did was a column vectors. It takes more work to going from non-column vector to that. So these are actually column vectors, and then we go to the matrix. What by what size? M by n, with the coefficient in this case is r, right? So what's the map? Phi of t is ascending to what? Some matrix, right? But t is that, and what is this m? What does it got to do with that? Where, what was the condition? T of v is given by mv for all v in Rn. So there was this map. Now this is a vector space in here, vector space, and I showed my solution of this function being linear, right? Okay, so what is it? Your first space. What is the null space of V? These are all the maps. T in there. So TV is going to be 0 map, right? It's a 0 matrix. 0 in the matrix world. Sorry about that. I'm in a rush. And that's... Is that right? The map that goes to the 0 matrix. Okay. If the matrix and it was related like this, T of V is given by the 0 matrix, not dot product, the 0 matrix V, where this is a matrix of m by n with all the 0 entries in there, right? So what is this? 0 vector, right? No matter what you plug in, and you're going to spit out the 0 vectors, right? So what is the conclusion about the T? T is a 0 map, right? T is a 0 map. So what's the conclusion about the null space of phi? I pull out an arbitrary map that is mapped to 0 matrix, and it says the map has to be 0, right? So therefore, it's a 0 map. 0 linear map is the only thing whose matrix is exactly 0. That make sense? So I think it's easier to see dimension. Well, because of that, it's injective. And if you read about invertibility and isomorphism, so injective and an and also surjective, that says it's injective. And surjectivity is clear. If I pull a matrix M, then you can define T being given by this MB, so therefore there's a linear map exists. So surjective, injective, so that's gives us invertibility. Invertibility is about the map, and these two vector spaces V and W there. These two vector spaces, this and that matrix, Mn F are isomorphic. You read about these terms, right? If these are isomorphic, their dimension must be the same, right? So what is the dimension of matrix Mn? All the ones and in each corner, and there are m times n slots, right? And m times n. Which verifies our first result. Today, I started the course with, if I have this n time dimension n dimension m, what is the dimension of this space? I was saying m times n. This is a different way of showing that. Using the null space, using the rank theorem, establishing these two maps, the connection between these two things is actually invertible linear map. Therefore, these two things are isomorphic. Although they look different, the linear algebraic structure is exactly the same. Therefore, dimension of this one is a dimension of that one. There's an alternative way to obtain this dimension result. But what we proved with the TIK is a lot stronger. I actually constructed the basis, not just calculated dimension. So they are more into that direction. It's a better result. But it is a sneaky result to get that number, the dimension of LVW, making the connection to the matrix using this phi map. Sorry about holding too long.